right, pre-calc, there is a much longer in-depth video over graphing sine and cosine, day 1 and day 2. I'm just going to kind of make a way shorter video to summarize a lot of the things that you need to know. If you need more help past this video, definitely go look at the longer video and find what you need help on and ask me questions as well. So for graphing sine and cosine, we're going to be talking about graphing these on an XY coordinate plane rather than just around a circle. So the first thing that I'm going to ask you to do is for sine and cosine, you're going to go and find the sine at each of these given angles. So in class, I would just like have you work on it. But today, right on this video, we're kind of going fast. So we're just going to talk about how the sine is the y value at each of these ordered pairs. For example, this ordered pair is 1, 0. So sine is 0. And then at this ordered pair, we've got, I'm not even going to write the x part. We've got the y, which is a half. And then the y here is square root of 2 over 2. We've got square root 3 over 2. And then right here at the ordered pair 0, 1, our value becomes 1. So now I'm just going to keep writing the sign. I'm not going to write all the ordered pairs. I'm just going to write the sign around the unit circle. We've got 2 pi over 3, and that would be radical 3 over 2, radical 2 over 2, a half, and then it goes back down to 0. Visually, if I'm talking about the sign being the y value, for example, at pi over 6, the y value is this long. At pi over 4, the y value is this long. At pi over 3, the y value is this long. And at pi over 2, it's 1. That's a length of 1 right there. So we can see that the y value starts at 0 and gets bigger and bigger and bigger. And then it starts to get smaller and smaller and smaller and down to 0 again. Then what's going to happen is the y value is going to be 1/2 again, except for since we're going down, it's going to be negative a half. So the negative is telling me that I'm going below the x-axis, and then the 1/2 is the length that it is. Here we've got sine is the length of square root of 2 over 2, square root of 3 over 2, but these are going down. That didn't even line up whatsoever, sorry. We're going down to get there. And then this one would be negative 1. Then we start to go back up again, square root of 3 over 2, square root of 2 over 2, then negative a half, and finally we are at 0 again. And then we can just keep going around and around and around and again. All right. In this table over here, I'm going to pick points that are going to be easy for us to graph. And if you look ahead at the graph, the x-axis has pi over 2 and pi and 3 pi over 2 and 2 pi. Those values right there are going to be easy to graph because they're on the x-axis. Halving that would be like pi over 4. And then this would be 2 pi over 4. And then we'd have 3 pi over 4. And then 4 pi over 4, and so on like that. But when I look up here at pi over 4, square root of 2 over 2 is not something that I can easily graph. It's a horrible decimal. It's an irrational number. So that one I'm not interested in graphing. Pi over 6, sine is a half. That's pretty easy to graph, except pi over 6 is kind of hard to find on this graph because it doesn't fit exactly in between any of these. So I'm not going to use that one either. In fact, there's just 5 points, 5 x's that I'm going to use. 0, pi over 2, pi, 3 pi over 2, and then 2 pi. These are going to be our key points for the parent function right before we do transformations, which we're about to also do in this section. Our x values are the thetas. The y values are the sine. of that theta. So at 0 degrees or at 0 radians, sine is 0. At pi over 2, sine is 1. At pi, sine is 0. At 3 pi over 2, sine is -1. And going back around to 2 pi, sine is 0 again. Now, if I keep using the quadrantal angles, if I keep using the x and y axis as my key points, it's just after this last 0, it's going to start repeating again. 1, 0, -1, 0, 1, 0, -1, 0. So this is kind of like one full cycle that I'm going to graph. So let me erase these. So the next thing we're going to do is we're going to put those points on the graph. So I got to zoom to do a better job, try to keep them on there. So 0, 0. Oops, I wanted to change color. There we go. So 0, 0. Now the next one is pi over 2, 1, and my y values are not, they're not like labeled what they are. So I'm just going to call this one 1 and this one a -1. At pi over 2, it's going to be 1. At pi, it's going to be 0. At 3 pi over 2, we've got -1. And at 2 pi, we've got 0 again. Now, some people will look at this and say, oh, it's a zigzag, but it's not. So what I have is I have it graphed on my graphing calculator. I'm going to show you how to do that on your graphing calculator. So grab your graphing calculator. I don't think mine's open anymore. Let me go find mine. Oh yeah, I accidentally closed it. Okay, so we're going to go to y equals, and this is from the old other class. I already had that done. So we're going to type in sine x. I'm just going to show you how to do it from scratch. You're going to go type sine, the button right there, and then X will be the button next to the alpha. So they turn red when I push them. So you can see what buttons I pressed because you can't see my fingers. Before we graph this, we want to change the graph so it's counting in radians for us. So you're going to go to zoom, and then you're going to choose zoom 7. 7, you're going to choose zoom 7, and that should fix your window. So I'll go ahead and hit graph. Actually, I can just hit 7, and it will graph it for me. And you can see what the sine graph looks like. What I want to show you, though, is what the x's are counting by. So if you click on window, it says that it has like the X max and the X min. I'm not worried about those. What I'm worried about is what are those little tick marks X is counting by. This says 1.57 stuff. We should recognize 1.57 because that is half of 3.14. So the X's are counting by pi over 2's when you hit that zoom trig. The Y's are counting by 1's. The scale is what they're counting by. So I'm going to go back to my graph, and I can see that that at 0, I'm gonna do some fun things here. At when we have a value of 0, the Y value is also 0. I'm gonna do second trace value. If I type in an X value of pi over 2, you can see that we have the Y value of 1. So you can see where my points are lining up. The points that I had on my notes are lining up with this graph. And what you should notice is it looks a lot like a sound wave. And sound waves are called waves because they're kind of like rolling, very soft, just really nice waves. And sine waves are called the same thing. They're called waves. So I'm going to go back here. When we connect these, you just want to be really careful and just make it really nice and relaxing waves by the ocean. They should not be zigzags. What I should have done was make my pen thicker. That would have been a lot easier for me to make this better. So what I'm doing is I'm coloring in one cycle of this graph. But there's nothing saying I need to stop and do one cycle. So since one cycle is one time around the circle up here, if I go multiple times around the circle, the pattern will continue, or I can go negative angles. And that's what I'm going to do down here. I'm going to go the opposite direction, and the pattern is going to continue. So I'm just change my color so you can see what I used or what I graphed with a pattern compared to the original cycle of sine. So the sine cycle is always mountain valley. It always looks like mountain valley. One full cycle of sine looks like mountain valley. It's almost like a S for sine. If I'm going the other direction and I have a mountain here, I'm going to have a valley next. So I'm going to go down, middle, top, middle. So I'm going the other way. And if I keep going, it'll go down next. So I'm going to, make my arrow go past that last point and make sure that I can tell it goes down. On the other side, it will keep going. We don't have any more space, so I'll just draw the arrow that shows it will keep going up. So you can compare that with the Desmos graph. It is a nice, smooth wave. Oh, I'm sorry. I meant your graphing calculator. We'll come back to Desmos in a moment. It's a nice, smooth wave that can go on forever. Let's see, back to this. So I talked about this pink being one cycle. One cycle. So the one cycle, when we talk about how long that cycle is, we're talking about the horizontal length of that one cycle. The horizontal length of one cycle is called its period. So down here, I'm going to fill in period. The horizontal length of one cycle. It's how long one cycle is. In the parent function, so before we do any, transformations, the parent function will have a period of 2 pi. So that's the parent function length. And you can see that from our graph. It starts at 0 and it ends over here at 2 pi. You think about one time around the circle, starts at 0, ends at 2 pi. The next word is the sinusoidal axis. The sinusoidal axis is a crazy long word just describing the midline. So this graph goes up, it goes down, but it always keeps hitting the center at the same y value, and that y value is 0. So we write the sinusoidal axis as an equation of a line. And for the parent function, it's going to be y equals 0. The amplitude, we hear amp, and I always think of like a amplifier. If you play guitar, electrical guitar, you have to plug it into an amplifier, and an amplifier would make it go louder. It can also go quieter if you turn down the volume, but that's kind of what I think about. So an amplitude in this graph has to do with how high up the graph goes and how down low the graph goes from that middle line. So we start at the middle and we say, how far up does it go? How far down does it go? It should go the same amount. These are congruent amounts because the midline is right in the middle. So the amplitude is the length above or below the midline, which is the sinusoidal axis. And then for this parent function, the sinusoidal axis, the amplitude is going to be 1. Just 1 unit above and 1 unit below. Okay, and then the last thing I can't describe to you in the parent function because it would be none, but the last vocab word is phase shift, and that has to do with a horizontal translation. And we have talked about transformations and translations, and so we'll come back to this phase shift just in a little bit in our notes. But for the parent function, it would be none. Okay, so now that is the sine graph. We're going to look at cosine. So cosine graph, you can go through and label all of the cosines at each angle, but for time's sake, I'm going to talk about the ones that we're going to use for the key points. The key points are going to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. So at 0, our cosine is the x value 1. At pi over 2, the cosine is the x value 0. At pi, the cosine is -1. At 3 pi over 2, cosine is 0. And then back again at 2 pi, we have a 1 again. So this starts at 1, 0, -1, 0, back to 1. So cosine and sine, they use the exact same key points. They just start at a different one. Not a different x, but a different y value. So let me graph cosine. And we're going to go ahead and make this 1 and -1 here. Cosine is going to start at 0, 1. Cosine is at pi over 2, 0. Pi is -1. 3 pi over 2 is 0. And 2 pi is 1. So the one cycle of cosine is going to look different than one cycle of sine. Sine kind of looks like an S. Sine looked like that. Cosine starts at 1, goes deep, deep down into a valley and comes back up. It's starting at the top of its mountains. You can go to your graphing calculator and go to y equals, and this time I'm going to graph cosine x, but I'm not deleting sine x because I want to see how they compare to each other. So since I have different colors, you can see on here that they look exactly the same. They're just maybe horizontally shifted from each other. Doesn't really matter which one is which, but if I'm looking right here at 0, and then the next place right here, I'm looking at pi over 2. So the blue one hits at 0. Actually, those don't line up. I'm lying. I'm looking at pi over 2, then I'm looking at pi. So for the cosine graph, it hits the x-axis at pi over 2. The sine graph hits the x-axis at pi. And they're exactly 90 degrees or pi over 2 apart from each other. Same shape though. So here's my initial one cycle. This is my one cycle of cosine. Looks like this. That was a terrible picture. It goes down, up. And then from there, it's going to continue and make mountains and valleys. So I'm at the top of a mountain right here at 1. So next I need to go to the middle, to the bottom, to the middle, to the top. So I need to continue that pattern. And then the next place it's going to go is down to the middle. So I'm going to make sure that at the end, my arrow points down. If you make your arrow point up, I'm going to take off. because that's wrong. It points down. The period, sinusoidal axis, amplitude, phase shift, those are all exactly the same for sine, for the parent function, as they were for cosine. So the period parent function is 2 pi. The sinusoidal axis, y equals 0. Amplitude is 1. Phase shift, we don't have one. So now we start talking about transformations. So I'm going to scroll. The rules for transformations of functions. This is just a reminder of all the stuff that we covered in chapter 1, and you should have covered a lot in algebra 2. Right here, I've got an example of all of the transformations and where they would be in a sine graph or in a equation, in a sine equation or a cosine equation. The A, the B, the C, and the D just represent different columns in which we will make a transformation table. One thing I'm going to point out to you is that the B has to be factored out of that C value, or you're going to have the wrong C value. We did that in chapter 1 as well. Make sure your B value is factored out. So I have this on Desmos, and you're more than welcome to try this if you'd like. What I did was I typed in an equation with the same variables from that picture, and then I made A, B, C, and D sliders. So this will give you the ability to see when I take my A value, this number out front, and I change it to be something other than 1. I got to turn this on. Hold on. When I change it to be something other than 1, this is just the sine graph. When I change it to be something other than 1, it is stretching it vertically. So the A value is going to give me a vertical stretch or possibly a vertical shrink. If A is 0, though, we have a problem because it's not a sine graph anymore. So that vertical shrink has got to be between 0 and 1. If it's above 1, we've got a vertical stretch. Now, if I go to negative, what ends up happening is you can see there is a reflection in the graph. There is a reflection. So if I'm at negative, that negative is a completely separate thing than the vertical stretch or shrink. Okay, and we can just have a more stretched but also reflected sine graph, the bigger negative number I have. So that is what the A value does. It's a vertical shrink or stretch, and if it's negative, there's also a reflection, but 2 separate transformations. My B value is next. That is inside of the sine. Here you can definitely tell it's inside because I had to put it in parentheses to graph it correctly in our notes. And a lot of times you're not going to necessarily see the B value inside of a parenthesis. You can always put it in one, but typically they don't always write the parentheses for that. So my B value, as I make that bigger, that is going to be a horizontal shrink. Right now you can see this graph is shrinking horizontally. It's kind of like an accordion where I'm squeezing it together. So again, if we're at 1, it's the same, but if I get bigger than 1, it's a horizontal shrink. Remember, horizontal is all like the not common sense kind of thing. Like it's the opposite of what you'd think it would do. So if I have a bigger number, it's causing the graph to horizontally shrink. And then if I go between 0 and 1, we now have a horizontal stretch. If I go to 0, it's not even going to be a graph anymore. If I go to negative numbers, let me just go to -1, it is not a flip up and down. This one is a reflection in the y-axis, which flips left to right. And it's kind of hard to tell what's happening here, but that's if I go back and forth, you might be able to tell. It's kind of hard to tell. But if you imagine lining up the red point with the green point, those are horizontal reflections of each other. Okay, so the B value is horizontal stretch or shrink, but it's opposite of what you would think. Now our C value, Our C value is inside. So this is going to be horizontal translation. So as I move my C value, you can see this graph is moving side to side. But what happens if I move the C value by 6.28? 6.3. It's not 6.28, but pretty close. If I move it 6.28, it lines itself up again because that's one full time around the circle, and that's where the cycle starts to repeat again. So it can also go the other direction. But there we go. No, I want to be at 0. Okay, and then the D value, that should move it up or down. Up, down. That one's pretty easy to see. The D value would have to be outside of parentheses if there's parentheses. If there's no parentheses, then D is the number out here would be D if there's no parentheses. What I should have said is the C value has to be in parentheses. Okay, so those are our transformations. And then this is where you would put them. You know, our A value, we would multiply by whatever's out there. Our D value, you would add or subtract here, whatever number that is. The B value, though, when we did this before, that's a horizontal stretch or shrink. And you know what? I have this in an example. I'm going to come back to that. I'm going to do it with example because with nothing there, it's harder to tell. But that's going to go in this column, and then the C column will have whatever the left or right transformation is. So what I'm going to do is skip a lot of this because, like I said, this is going to be a very condensed version of the notes. So I'm skipping a lot of this vocabulary. I kind of went over it. Haven't really showed you how to find it if it's not the parent function yet, but I will do that on the day 2 notes. So I'm just going to skip all of day 1 notes. Or maybe I'll skip. No, I want to skip all of day 1 notes. So there's plenty of them. There's lots that you can go watch the video on. Yeah, I'll just go to day 2 notes. So day 2 notes, I kind of wrote how we find the period, sinusoidal axis, amplitude, and phase shift in here. You can read that. I'm just going to do 2 examples. So we'll start with this one right here. And the first thing that I notice is that this is a sine graph. So my x values are going to be those key points. My sine graph, or my sine of x, that's going to be my y values. So I think about sine being the y values as we go around the circle. So if this is 1, 0, this is 0, 1, negative 1, 0, 0, negative 1. The sine values go around the circle from 0 to 2 pi, and it's the y's. So we start at 0, 0. We go to 1. We go to 0, negative 1, 0. Okay, if you want to memorize these, you can, but they start to get confusing when cosine has the same numbers, but in a different order. We haven't done tangent or cotangent or cosecant or secant yet. So they start to get confusing. If you want to draw one of these graphs just to help you know, that could also help. You got to figure out what works for you. Now, in this equation, I notice that I have only stuff on the inside. So I have like the B and the C. The problem is that they are not separated. This is not in that formula that is right up here that says that B has to be factored out of x minus C. So I don't have that. So we have to factor first. So to factor, we're going to undistribute. So right here, I'm dividing out 2/3. So my equation is going to be y equals sine. I'm going to have 2/3. And then I'm going to have x minus, and we have to find what pi over 6 divided by 2/3 is. So I'm going to just go off to the side here. Pi over 6 divided by 2/3. You can't divide by fractions. Instead, pi over 6 multiply by the reciprocal. When we multiply by fractions, we go straight across. You do not need a common denominator. 3 pi over 12. We always reduce fractions if possible, pi over 4. So this is going to be pi over 4 right here, close, close. So that's the equation I'm going to use to find B and C. I think I'm asking you to do transformations somewhere. I don't know if it's on this. I don't think it's on this one, but I think it's on the assignment, perhaps. So this 2/3, the B value, that's going to be a horizontal. And then it's going to either be a stretch or shrink, which I'll come back to in a second, by a factor of 2/3. Nope. By a factor of something. Because it's horizontal, we're not going to use 2/3. Because it's horizontal, we use the opposite operation or the inverse operation. And for this, it's the reciprocal. So I'm going to be using a factor of 3 over 2. 3 over 2 is greater than 1. So this is a stretch. So in my table, my B values, that's going to be multiplying by 3 over 2. Okay. And then using transformations, talking about this minus pi over 4 over here, that means I'm going to add pi over 4. For transformations, that would be translate right pi over 4 units. So that would be that transformation there. Remember, it's always the inverse operation. So if this is subtraction, I'm going to do addition. If it says subtraction, I'm going to the right. So now we can fill out our table, and some of you are going to struggle because you have to be able to do fractions. 0 is easy. Okay, 3/2 times 0, that's 0. And then add pi over 4, that's pi over 4. That one's easy. Pi over 2, we have to multiply that by 3 over 2. So I'm just going to go over to the side here. 3 over 2 times pi over 2. We multiply fractions straight across. I get 3 pi over 4. Pi, I have to multiply pi by 3 over 2. If you're multiplying something that's not a fraction with a fraction, you got to put it over 1. Multiply straight across. We get 3 pi over 2. Then I've got 3 pi over 2 multiplied by 3 over 2. And we go straight across. 9 pi over 4. And then finally, 2 pi over 1 times 3 pi over 2. That gives me 6 pi over 2, which reduces to 3 pi. So that is my times by 3/2 column. Now, adding pi over 4, if I add fractions, I have to have a common denominator. Since there's I'm going to change colors. Since there's nothing going on over here, there's no what are these called? Vertical transformations. I'm just going to put my work over there. So 3 pi over 4, we're going to add pi over 4. You have to have same denominators and keep that same denominator. We add the tops and we get 4 pi over 4, which reduces to pi. The next one, 3 pi over 2. I'm going to add on pi over 4. These do not have common denominators. So I need 4 for my denominator, which means I multiply this one by 2 over 2, and I get 6 pi over 4 plus pi over 4, just 7 pi over 4. Now we've got 9 pi over 4 plus pi over 4, and that's 10 pi over 4, but that reduces to 5 pi over 2. Finally, 3 pi, which is over 1, plus pi over 4. I need to make this 3 pi have a denominator of 4, so I'm going to multiply it by 4, and that makes my top 12. And so I get 13 pi over 4. You can probably figure out some of these without doing all the math because the x's are spaced evenly. Whatever that space is, the x's are spaced evenly. So if I go from pi over 4 to, if I go from pi over 4 to 4 pi over 4 to 6, that's not right, to 7 pi over 4, hold on, this is 7 pi over 4. If I'm going up each time by 3 pi over 4, I can figure out this one would be 10 pi over 4, and then this one would be 13 pi over 4. So I can save myself a little bit of time by noticing what they're going up by. They're always evenly spaced. All right, graphing. I'm going to graph these, but there aren't pi over 4s on the graph. So we want to work smarter, not harder. I'm going to graph the ones that, to me, are easy to graph. This one looks easy to graph because pi is on my x-axis. 5 pi over 2 is also on the x-axis. And pi over 4 is pretty easy to find on the x-axis. So I'm going to go over here. Pi over 4 on the x-axis is exactly in between 0 and pi over 2. It's that 45 degrees where pi over 2 is 90. Pi over 4 is 0, so I'm just going to put a dot exactly in between. Pi is 1. 7 pi over 4, I'm not sure where that is, and you can figure it out and count them, but I'm just trying to give you shortcuts. So 5 pi over 2 is on the graph, and that's at -1. And then 13 pi over 4, I don't know where that is either. But what I do know is that these are evenly spaced. So if I look horizontally from this dot to the next dot, they are 1.5 blocks apart, 1.5 blocks. So that means my next point is going to be 1.5 blocks from the previous point. Oops. 1.5 blocks from the previous point, and the y value is 0. Another way you could look at finding this point is that it's exactly in between of the 2 points that I knew where to put them. It's exactly in between, and the y value is 0. And then finally, 13 pi over 4, 0. These are 1.5 blocks apart, so 1.5 blocks further, barely off the graph, I can handle it, at 0. So work smarter, not harder, when you graph these. This should have that sine shape of the one cycle of sine. And to me, it looks like it does have that kind of S shape. So it gives me a good idea I'm doing it right. Then I need to complete the entire graph by following the pattern. So each point horizontally is 1.5 blocks apart, and it goes valley, mountain. So I'm going to go valley next. So 1.5 blocks, 1.5 blocks in the middle, 1.5 blocks at the top, 1.5 blocks in the middle, and so on. And then I'm going to do my best to make a nice smooth what is this called? A wave, nice smooth wave. That one maybe wasn't as pretty as normal. Then we fill out information. So above here, I tell you how to find the period. I'm just going to say it out loud, but it is written above. The period is always the parent function period, so 2 pi, multiplied by whatever we multiplied our transformation table by. So I multiplied it by 3/2. The period is going to be parent function multiplied by that B column value at the top. So when I multiply that straight across, I get 6 pi over 2, which reduces to 3 pi. So if I look at my graph horizontally from start to finish, from here to here for one cycle, it should be exactly 3 pi long. The amplitude, that is on the graph how far up and how far down from the midline. In my notes above, I say the amplitude is just a vertical stretch or shrink. It's the factor that you'd multiply your y's by. Because I did not have a vertical stretch or shrink, the amplitude is 1. The sinusoidal axis, the parent function, the amplitude for the parent function is 1, and we didn't have a vertical stretch or shrink, so the answer is 1. That's what I meant to say. The sinusoidal axis parent function is y equals 0. This gets affected by the d value, or your transformation up or down, which we did not have one. So it is still at y equals 0. And then the phase shift, we did add or subtract in this last column, that C value. It says add pi over 4. You will answer phase shift with direction and amount. So we're going to write the word right 4, or pi over 4, right? Pi over 4. Domain is all the x's and all the y's. We're doing this in interval notation. So when I talk about this arrow going and we keep repeating this pattern over and over again, your domain is going to be negative infinity to positive infinity. Remember, we have parentheses for infinities always. The range would be from how far down to how far up. So when I look at this graph over here and I think about how far down to how far up, like the graph stays in this little region the whole time. So the lowest point would be -1 and the highest point would be +1. And it does equal -1 to +1. So we will use the brackets. These have to be in order from least to greatest, or you will get it wrong. We always go from least to greatest. Okay, I'm going to do one more example. And then, like I said before, there's lots of more examples on the longer video. I just decided to make a shorter video so that you could get through this as quick as possible. So I'll just look at, we didn't do cosine yet. Okay, I'm going to look at number 3, and it is a cosine. So in my table, I'm going to think about my y values being the cosine of theta, or the cosine of x in this case. And if I need to refer to those key points, 1, 0, 0, 1, -1, 0, 0, -1, the cosine is all the x values. So 1, 0, -1, 0, 1. Then we look at our transformations, and I have a reflection in the in the x-axis. I have a reflection, and I also have a vertical stretch by a factor of 2. Those do not get put in 2 places. They get put in 1 place and you just multiply by -2 at the same time. While I'm talking about that, vertical stretch or shrink affects our amplitude. So the stretch or shrink by itself is 2. Our amplitude is going to be 2. The negative has to do with reflection that does not affect how high and how low it goes. Let's see, we come to a parenthesis next. So in our parenthesis, we've got 2x plus 2 pi. So what I have here is something that needs to be factored out. So we have to factor out 2. So my new equation, when I factor that out, -2 cosine 2 parenthesis x plus pi, close parenthesis, close parenthesis. That's going to give me my B and C amounts, but remember they're opposite. So where I see a 2 here, I have to multiply by the reciprocal. Oops, I spelled that wrong. Reciprocal. And the reciprocal of 2 is 1/2. So that would be a horizontal shrink by a factor of 1/2. And then this pi over here is a translation. And this is going to be left pi units. So in the C column, we go left. Okay. Down below, let's see. The sinusoidal axis is still y equals 0 because we didn't do any up or down transformations. Our phase shift would be left or right. This one's going left, 2. The period is going to be affected by the times by 1/2. So the period, I take my normal parent function period and we multiply it by 1/2 and we get our period is pi. Domain is always going to be all real numbers. The range, I don't like to get that until I've filled out my table because I need to know what the highest and lowest values are. So let's see. -2, 0, 2, 0, and then -2. So here we've got our highest value at 2 and our lowest value at -2. 0 is in the middle. So that's where our range is. And then the rest of this is fraction work. I'm going to skip this because I want to make sure I talk about one of them that has a D in it. I should have picked one already. Oh, I guess it's this one. So this one right here has all of the values represented. It's already factored. Yay, it's already factored. This one is a sine. So we're going to use our y values. So we're using the y values. I just copied this right down there. So I'm not going to rewrite all the numbers again. It'd take a long time. I'm just going to put my sine values are 0, 1, 0, -1, 0. The a's we're multiplying by 3. So 0, 3, 0, -3, 0. The d's are subtracting 2. So -2, 1, -2, -5, -2. The b values, because there's a 1/2 here, we do reciprocal times by 2. And then the c values, we do opposite of add pi over 2. We're going to subtract pi over 2. So I'm going to fill out the information to show you how you can fill out the information. And I will go ahead and graph this one at the same time, or well, not at the same time, but I will graph it as well, just in case if you need the information that you don't need the graph, you could, sign off early. So finding the period, we always start with our parent function period, which is 2 pi, and then we multiply by what we multiplied our x's. And now our period is 4 pi. Our amplitude comes from our vertical stretch, which is 3. It's always a positive answer. The sinusoidal axis comes from that D value. It's going to be y equals D. So we have y equals -2. Because originally it's at 0, this one went down 2. So there's that like sinusoidal axis. You don't have to graph it. I'm just trying to point to it and you can't see my hands. Phase shift, we look in our C column, that goes negative. So that's going to be left pi over 2. The domain is all real numbers. Or, I'm sorry, did I write all real numbers on the last one? Or did I do negative infinity, positive? Oopsies. Sorry. Get confused between classes. Negative infinity to positive infinity. Go back up. So this is going to be negative infinity to positive infinity. And then my range, that's going to come from this D column. And I'm looking, my lowest number is -5. My highest number is 1. So we're going to go from -5 to 1. So let me finish filling this out and then I'll graph it. We're going to multiply all of these by 2. So we get 0. If I multiply by 2, it's just the top and I can cross reduce pi. Then I get 2 pi. Then I get 3 pi. And then I get 4 pi. Then I'm going to subtract pi over 2 from each of these. So this will be negative pi over 2. If I'm at pi, and I subtract 90 degrees, I'm now at pi over 2. If I'm at 2 pi and I subtract 90 degrees, which is pi over 2, then I'm at 3 pi over 2. All right, these are all evenly spaced. So at this point, it looks like we're going up by 2 pi over 2. So 5 pi over 2, and then 7 pi over 2. You can also just, actually use subtraction to find it. So negative pi over 2 is -2. Pi over 2 is 1. 3 pi over 2 is -2. 5 pi over 2 is -5. And then 7 pi over 2 isn't on the graph. If I'm looking at how these are evenly spaced, let me start connecting this here. These are evenly spaced 2 blocks apart. So if I imagine 2 blocks, it would be about here. So I can approximate where it is. But it doesn't really matter because after that, we're going to follow the pattern the other way anyway. So here I'm at a mountain. After a mountain, I go valley and I go all the way down to -5 and I go 2 blocks horizontally. 2 more blocks horizontally and I'm at the midline. 2 more blocks horizontally and I'm all the way up at 1. So you need to connect until you're off the graph to show me that you can continue this pattern correctly. Okay, I think that's about it. There are, like I said, more videos, and there are 2 days of worksheets. You have all of today plus all of the next class to be working through these worksheets. Have a great day.